So it says, just need to find the event to make sure I can confirm that I can see everything's working there. I don't know if I'm talking to myself twice or not. Here it is. Please work this time, Google. Cut me a break. All right, I'm gonna check the volume real quick. Yep. All right, so and I'm gonna say okay to that. Just gotta say okay to a couple things that Google's making me say okay to. All right, you there yet, Dawes? You there yet? You chimed in yet? I'll jump right to the to torque or not to torque yield bolts. The bolts. I'm gonna see if you pop in or not. Dawes. Let me. You got it. Where are you, Dawes? Or is it Lunar? Lunar and who else? All right, jump into it. Okay. So I've looked at a few of these blogs now about torquing or not torquing, not the other torquing, but this torquing. And let's get right to the blog here. Looks like a really nice blog. They're telling you to go ahead and use them. I would tell you yes and no. I would tell you no. And ultimately, I'm going to tell you no. But I have to show you why no, right? You want to see why no. Oh, you can't see my screen. Let's do this. I'll get you into my screen in just a second. But let me just jump into this. This is the Class A bolt, 8 bolt. And that's what the an error occurred. Really? Now I see it. So we're still here. Okay, Class 8 bolt. 1, 2, 3, 4, 5, 6. That's pretty much what these head bolts are about. They're a Class 8 bolt. Now, we got to get around to the yield thing right quickly. What do they mean by yield? So I'm going to show you share my screen in just a moment. Before I do that, the bolt is elongated. It's stretched, however you want to think of it, but it's elongation. When this goes into the block, and then you get in so far, the back of this now, as you're still cranking, this will still thread in. And as it's threading in, it can't go anywhere. This part can't go anywhere anymore, and this starts to elongate around there from that point where it's anchored all the way back. Wherever it tips, wherever it gets into the block, minus the block thickness, so it might only be this much. I don't know how much is on each bolt that you get. It would matter though. You would want the most amount. Now, what happens though? We have elastic is when it goes back. So I can crank this in here at say, I tell you what I can crank it in at. I wrote 55 pounds or 52 foot-pounds. So I can do that 52 foot-pounds. I'll only be at 91% of this bolt's capacity. I'm sorry, 70% of the bolt's capacity at 91,000 PSI of clamping force. It's pretty, clamping force is going to be a little differently. But I'm using 91,000 PSI of this bolt. And I've got the clamping force of around, I think it's 700-800 per bolt. Now, clamping force gives you that ability to clamp down, right? A clamping force. Don't get confused with the PSI. Let me dump out of this now, and I'll go live onto the video. Oh, okay. Before I do that, though, this is a 325 bolt. This is a structural bolt used on bridges. It shouldn't be used anymore. I don't know how it would still get on a bridge. Maybe you can still spec it somehow, and it still gets on a bridge. But the tolerances on this bolt are pretty darn good. Let me see if I can show you. I'm gonna try to wiggle this a little bit. You see it? And then I'm gonna push it. I'll push it back and forth in line. And that's That tolerance is up there at, let me look at my notes here to give you a thing. That is at 6.697 on the nut, and on the tolerances of the thread are at 0.6806. That matters because, again, I'll show you why in a second. You see I'm pushing back and forth. Now I'm going to show you a bolt that is class A under A and B. So A is your bolt, and B would be your nut. Now watch this thing. See that movement, that track? I can move back and forth, and the sloppiness of it. That's the difference in quality. This is not marked. That puts it way up there at a class. This is with the class 1, class A bolt. That's the shit quality. Now, before I go on to that one, gulling. Why another reason why you should not consider reusing a bolt is that gulling can happen. Guys can look up gulling, but it mostly with stainless steel and other products surely can have it also. But you're tightening this into your block. It's not quite bottomed out yet or you can start pulling your block down, and all of a sudden you feel a resistance. Should you keep going? No, you've got to back it out. You should then break out a thread, and you should start tapping it. You should retap your opening, and possibly even do a runner around your nut. The tap you want to use, this is a bottom ending tap. It pretty much flat at the bottom, see it? And it will go to the bottom more, not the one with the beveled head. That one won't get to the bottom. You might need that bottom with your design of your block. I don't know. But that would be the more the tap you want to use. So now you see the quality of that is what really sucks on something like that. And the class 8 bolts, they step it up where they have one of the better tolerances, one of the best tolerances, unless you get something else custom beyond that. And of course you have matching nuts, but you don't have to worry about that. And this is above a class. This is an A325 bolt. So if you really want some high tolerance quality stuff, you step your bolt up to a different one altogether if you can find it. Now let me share my screen. Just now, I'm going to share my screen. I'm going to bail on this. Let me make sure no one has anything to say before I jump away. Hey, Doss, cool. I'm glad you're back, man. Cool. So, you have nothing to say. That's the bolt. It elongates. It does not go back. Once you pull something into the yield strength, if I elongate this just by micro amount, doesn't matter. I'm sorry, if in elastic mode, it will keep going back, and I'll show you on the scale. But in plastic mode, it will not go back. But not only will it not go back, you'll now have maxed out wherever it failed, wherever you had it last torqued at. If you can do the calculations and figure out what that bolt is, and I'll show you the bolt. Let's just jump out of here and let me jump right to it. So I want to screen share. So now it should be screen sharing. Hopefully I'll see it pop up just now. Yeah, we're on the money. So now I'm screen sharing. So now you see that what I was talking about, what tolerances of a bolt of your 0.692, your 0.67. This doesn't seem like much, but I showed you just now the sloppiness. That was a 1B compared to the structural bolt for bridges. The one I showed you with that big giant one was what they put on bridges, A3205. And your tolerances are down there. Your class 8 bolt's pretty close to there also. Now I want to show you, I ran across a bunch of blogs. I'm trying to find a guy's blog real quick. And blog, we'll get to this here. Oh, let's just do this. So let's jump right into what yield is. So elastic, it can go up here. You can crank it into, say, 100. Oh, I'll tell you what you can crank it into. So these bolts are about 7/16 that you're putting down there, maybe not. And we're looking at grade 8. I'm going to show you where some of them you can reuse, like for a Chevy, for example. But let's jump over. And so right now that that operating bolt of the 7/16 bolt that I showed you, it can do 12,800 pounds is what its proof load is at. That's PSI. Now we're at 15,900 on the tensile. Wait a minute, I got my wrong page up for you guys. And where's my course thread? 7/16. Stress area square inches, proof load, grade 2, grade 5, and grade 8. Let me scroll over one. And I'm going to work my way over to it. 7/16, grade 8, 52. These are foot pounds. It's going to matter to you because we're going to come back to that. And also here's 58. That's a fine course. That's a fine thread. We're using coarse. We're not using fine. But if you are, you can switch the scale over. But here's 52. That's going to be something to pay attention to. This is stainless steel. This is grade 5 and grade 2. This is what's going in the motor head. 7/16 or something around here, right? 52 and 80, 58. These are, again, are foot pounds right there with my mouse. Let's jump over. Again, so your 7/16 bolt, your decimal equivalent is 0.4375. I'll keep that handy for us. Let's jump right into our head bolt. This is where I get the 7/16 from using off of the jegs, whatever.com, jugs.com. And we have 7/16 bolt 14. 14 thread count, right? So there we go. Don't need to bother with that, but we can. 65, we'll just play with this one for a second. It's not all encompassing, but it gives you a rough idea of what clamping force you're getting out of 65 foot-pounds, 0.473 bolt with the coefficient of friction. You got to add that. If you're putting oil on it, you're really going to change your torque, what's happening in there. You're going to increase it like crazy. So if I were to do like 0.50 and do this, the clamping force went way down, but my torque and everything stayed the same. I lost clamping force. So be careful when you're adding the oils and all that. You're going to lose what you wanted, and everybody's soaking them in things like that. And you'll see this engineer, this car builder over here is going to say how, whatever. Look, here it is again. The cylinder head clamping pressure, 65 pounds. And you just saw me jump on that one there. We come back here. Here's our grade 8. Where are you? 1, 2, 3, 4, 5, 6. Right here, grade 8. So we're proof load. We're at 120,000 psi that we can take. 120,000. The working load is at yield. It's going to be 130, and at failure, it's going to be 150. So you guys dealing with yield belts, I'm going to show you how this works with the formula, how you know whether or not to play with it or not. But first, let you read this. I'll pause it, and that way when I explain to you, you also understand it. The yield point is a point on a stress strain curve that indicates the limit of elastic behavior. That means it can return. So this can return. I can do this all the way up to, let's say, 119,000 psi. I can load it, unload it, load it, unload it. Not forever, it's going to have fatigue that can happen, especially on this new heated temperature. I think you're at 400. So who knows what's going on there? Nobody's really testing these bolts afterwards. There's 400 or 200 sustained heat, 200 degrees roughly. Does that retemper this to a more brittle condition? Nobody's really taking them apart and testing them like that. But many people have lost a bolt inside there, and that's because they went past its limits. And we'll get to the limits. So this guy over here, see what yield is the point of stress strain curve that indicates the limit of elasticity. Elasticity. The yield is a point of a stress current that indicates the limit. You're done. And the beginning of plastic behavior. It's done. When you get to yield, you're done. You're in plastic. And let's go here again. So this is, let's say, right up to here is your 100 and your working range, your class 8 bolt, 120,000 load PSI, right? Back to here again. So here's your 120,000 right up to here, up and down, not, a couple, you only want to take the heads off once or twice, 120,000. You're awesome. You're okay. You cross 120,000, that bolt is proofed to show that it will now, you've been yield, you're done. So you try to get 120,000 again, and you walk away and say that same torque, but you've already had it to this torque. So say this is 120 and this is 122, right there, 122,000. Well, you're done. You can't put it at the, and you say that torque there is at, say it's at 65, just for, me rounding up to the numbers we know. And this was 65. Now your next step up on the torque level says go to, well, it's 65. Yeah, that's kind of I'm trying to make sure I word it right. So if this is 65 and that you 65 was here and you crossed the line, you went to 67 up here, and that gave you 67 foot-pounds, and you now are at 122,000. If you now torque this at 65 instead of the 67 on your torque wrench, you will have 120,000 pounds of force, roughly, of tension on that bolt. You will not, and not only that, you will have, watch how I follow this, you'll probably have nothing on that bolt because it's no longer elastic. You need to be back here at 67 for this to even start biting again. So if you make a mistake and drop down, you will have nothing. You'll think you'll have something that'll feel snug because it's so close. But if you just cross that line, that torque a little bit, and you cross it into the yield zone, you can only go from there up and then to failure, and then it drops down. Right about here is failure, and then it's just dropping off. I don't know what your torque this bolt, but we can say, I do know if we're going to show you on a scale here, and you're going to match it up with every car you have, and you'll give access to these scales. I'm going to give them to you. But let's say this is 120. 130 is your yield on this one. So here's kind of a small window here to work under, but it's available. So it's available up to the 130 on this one. Minimum yield strength. Well, I wouldn't say 130, it's saying it, but you better give yourself a margin of error and be under that. 127, or even more than that. At this point, you're at failure. All this from 130 to 150, you're playing around with danger. And this is where the bolts, fail, because all they have to really give you is this, that you're not supposed to be in here anyway, unless it's designed for that, and that's going to be the yield bolt. And why yield bolts work in a head condition? Well, let's go to this guy and let's hear him say it wrongly, and then I'll tell you why he's wrong, and then we'll explain. So let's see.
They're thinking, well, I had a 350, we tore it apart, cleaned the bolts, put it back in, everything's fine.
Bluetooth disconnected.
Big issue there is between those engines and the engines we have now is the aluminum heads and a particular type of gasket that they have now called a MLS gasket. MLS stands for multi-layer steel gasket. If you look at this gasket, I know it's kind of hard to see, but this is made of several different layers of steel sandwiched together. And it does it with it back.
So let's go back with this one now.
And your head bolts are loose. You blow a head gasket, you've got to blow gasket. These torque to yield head bolts, the way a normal head bolt, when you tighten it down to a torque spec, it is designed to stretch a little bit, not very much, because it has a very limited elastic limit, which is how far it can stretch. Torque to yield bolts, they are designed that when you torque them down, that they will stretch, and then they will go back after you.
Right there. And then he says they'll go back. This is where he's making a mistake. He's not the only one, but let's just stop that because I don't need to show you any more of that. He's got 17,000 people followed him. There's quite a few people who are praising him. Thanks, man. I was confused about that. Now I'm going to get my heads back together, etc. All right. They are designed not to come back. Where the advantage of that is that, let's go to another image so we do that. Where the advantage of it not going back is that the heat, you do not have to worry about it stretching anymore. It's now a controlled, it won't stretch. Heat won't bother it. It will not be elastic. It will be a firm piece of metal in there at whatever torque it stops at in the elastic. Yeah, in the plastic mode. And let me grab one for you. Let me say yes to that. Scroll over. Where's my man? Damn it, this engine block guy, this engine machine shop guy I'm trying to find. This, I was going to get to this. This is the coefficient part I'm going to talk to you about. Okay, this guy right here. So basically, he says, and in between, elongate much while achieving its compound. One stud may stretch this much to achieve 20,000 pounds of clamp load. The other one may stretch this much to get the same amount of clamp load. This is true. Based on you can reuse any bolt as long as you don't get into the yield of the bolt and stay within 80% of its yield strength. This is this guy's position. Well, it's actually the manufacturer that tells you what he wants you to do in there, if he wants you to go into that yield. And the yield to yield requirements are what they wanting sometimes. You know, where they say, let's see where I got this damn thing at. Torque to yield, where they want that. Do the threads change on torque? They do. The more, the finer threads will give you more torque, Doss. So yielding is when, did you see it? Yield, I guess I just saw your comment. Did you understand it? So yielding is up here. It's no longer going to be elastic. It will not come back. Right about there is where I'd stay off on this one, where I'd stop, where it's going to keep coming back. But the disadvantage of that, you put it in a motor mount, right? And you tie it down. The motor mount doesn't have enough clamp, the head rather, right? The head on it, it needs more clamping force to resolve the heat that comes in there. So if you say you have it here, and remember this thing at this point is still elastic, meaning it can still stretch. It can still stretch without breaking till you get to its yield point. So let's say you torque this down, a yielding, a bolt that will be elastic. And say the manufacturer said, I want you to put a yield bolt in here. I want it to yield. I'll explain why in a second. But you put an elastic bolt in there, one that can, because you're like, you know, I'm going to be able to reuse this bolt. It's going to be able to expand back and forth. Here's the problem. The forces from that head, the pressure, the heat, and all that may cause the same amount of torque, if you will, on the underside of this bolt head and start pushing it away because it's still in elastic mode. It can push away literally. And then your head's leaking, and now you got oil everywhere, and then the oil comes in there, maybe some fluids, and now you got a blown head gasket because you use an elastic bolt here. And when they wanted you to go into the yield, now you see why the yield? So same head, but this time I take that same bolt into a yield position where now it no longer is elastic. It will not come back. So now it has that clamping force on there. This head tries to expand, and it will get nothing out of this bolt. It will not stretch back anymore. It has no more rubber band effect. Think of it as a rubber band. You pull a rubber band all the way out. At some point, Doss, you can no longer pull a rubber band anymore. It will break at that point before it does anything else. But it will not come back anymore. As long as you hold both ends, that it has no more elasticity in it. This is where the advantage of a yield bolt is with something like that condition. Your manufacturer, your motor would tell you that. Now let's jump away from that. Let's finish with this guy here. He's an engine builder. And let's see his comments. And his comments are dealing on this. And he needs some badass bolts. Some of the most stressed out parts of the $1. So no matter what the applications, there is nothing faster. Okay, let me run on. Tensile strength fatigue is very important because that's why another reason you shouldn't put it back. You don't know what that bolt went through in that engine, what kind of heat rate, you know, the heat cycles that it's going through. You might be able to reuse it, but why take the chance? Because remember this, that when you thread a bolt in and you're creating torque in those threads, and you know how you pop a head off of a bolt. Sometimes you're like, oh man. Well, and then you try to easy out it and it doesn't work. That's because that torque is inside those threads still. They're inside that thread. So if you got it up to, 500, 700 foot-pounds of torque inside there of clamping force or tension or whatever, it's you got to get it off those threads, and it's not going to be easy. So the best thing is pack it up and take it to a damn machine shop and let them drill it out. It really is one of the best things to do. And also if it's got gulling in it, that will really lock it in there also. Okay, torsion strength that's torque, right? Proof load, and he makes a mistake here also. This is correct, the proof load, and that's what you see here. And we go over to here. And maybe I went too far on that one. This will be a proof load. This is where you can play around with going up and down, up and down, up and down, and you're good to go. And now where it cannot return to, right. Or fasten before it goes into plastic range, where it cannot return to its original size and shape. That's it. So whatever it took to get to that plastic mode also is a permanent lock-in. It's done. So if you took it to 70 psi, I'm sorry, torque-wise, if you took it to 70 foot-pounds and it became plastic, that bolt is totally ineffective again for clamping again until you at least get to 70 and some change again. It's done. So anything under 70, it's not clamping jack down. You got to have 70 on it again. So this is where everything can go wrong too. Where it cannot return to its original shape, size, and shape. That's correct. On this side, on this point of yield, permanent elongation of the fastener sets in. This is correct. If you continue to load the fastener, it will reach an ultimate tensile strength in which necking or elongation occurs. Well, if necking causes elongations there, until it stretches to the point of breakage. Yeah, whatever. Right. Okay, your shear strength, we don't have to worry about that. So here he's talking about the Class A, right? These bolts are often used for OEMs. They're 150,000 PSI. That's true. One of the issues with grade 8 bolts is that there are some areas where you really don't want to use them. If there's a cylinder load on them, cyclone load on them, could start to get into trouble. This is where... So you can use it on a cyclone load. So this one is one of the things I found to be wrong. You can use them on a cyclone load. They're going to be engineered bolts of the grade 8 style that handles that. And that doesn't matter about the alloys because, again, the manufacturer is going to tell you which one you should be playing with. Don't worry about that. There's something else in here. There's definitely a relationship between torque and preload, but there is some confusion as to the difference. When connecting rods, it is not too difficult to use the stretch method and to measure the preload by measuring stretch. It's very difficult if you plan on measuring stretch on that bolt. So this would be amazingly difficult. But in head bolt, it's much more difficult to measure, and you're basically relying on the torque wrench to stretch the bolt. A torque wrench needs to be calibrated often, and I'm just trying to scare you. Don't worry about that. Lubricants. All right, here's the part where I think he made lubricant. Maybe this was it. I thought it was that one. There's a huge difference in torque depending on what type of lube you use, whether it's engine oil, extreme plus lube, EPL, which is used quite a bit in NASCAR, for instance. Trapp says, yeah, they're experts he's talking about, technology doesn't recommend any particular type of lube. We normally recommend that the higher the torque is, the more efficient lube you use. So here is a crazy statement there. It's better for the fastener and the torsion stresses. Friction can take up at 80% of the torque to overcome. So the more you can reduce the friction, the less torsion force you will put on the fastener, and the more efficient your stretch. You'll stretch the stud, which is really the goal. This is 100% wrong. Don't do that. Do not lubricate if you can help it. You clean those threads off, etc. Here we are on friction control. If we come to it's a coefficient. It's a coefficient, typical coefficient of friction and power screws. This is just something typical that I'm just showing you. So if you were going into cast iron, you change your coefficient. You go into brass, you change it. That means you would 0.21. You would lower it by this much if you use this lubricant. Here's oil. Now it's saying on this scale 0.12, 0.18. That's being nice. That's being nice. And snap, do it. Oh, this guy. So he gets to come up here too. So this guy says tips for using head bolts. Remember that guy, just the engineering, the guy who does the engine manufacturing. He said reuse the oil, load them up, right? Reuse is not usually recommended by dealers and car manufacturers. However, when you change your head gaskets or other mechanical work to the head assembly, you can reuse your head bolts if they're in good condition. And you follow a few tips. Clean and inspect, soak in oil again. I'm going to stop there. This is not what you want to do. You really have to know about that bolt. And I'll explain it to you and wrap it up with this video now. You've got to know, first off, using a grade 8 bolt, what size. It's going to change your your specs. Then we have, so in this case, we're going to use a cylinder head bolt. It says 65 foot-pounds is going to be your cylinder head torque to it. You're going to remember that. Now, again, what if I put 65 pounds in your torque? The metals matter too, but I converted to the 7/16 bolt to 0.47375 millimeters. And I did a coefficient of 0.20, which is just steel, basically. You know, I'm practically, I gave it some minor lubricant issue. Now my clamping force again. I recycle it. My clamping force is beautiful, holding that head down at 742 pounds. Now let's go. I'm going to come back to that. Let's go to the guy. He said oil it up. I gotta have my oil chart here. I hope to show you guys oiling. Great. That's just great. That's tempering. That's how you're making this bolt, this classy bolt, this classy A. It's gonna get tempered. This is another way. This is a proper way to figure out your torque. This is gonna be too difficult for you to follow, though, to do the proper torque for that bolt and coefficients and also the friction. That is gonna just be too much data. It's the one we just did, and I just happen to have it in another page. Yeah. Got to show you the oil. Well, let's come here. If you're going to, here's some nickel anti-siege. It's got a nice low coefficient of 0.13. I recommend maybe perhaps trying this. Now, that might work out a lot better than the other stuff there. I'll give you the link to this anti-siege lubricant. I am going to get hold of this manufacturer on this other product about something, but where the hell is my damn... I'm going to hit it. It won't let me jump out of that one. I'm going to hit friction real quick with oil, coefficient of, yeah, let me just do that real quickly. I want to scale really. Bear with me. Let's try a chart. This was the head gasket stuff the guy mentioned. I just triggered on it rather. He was talking about head gaskets that they allow. His theory was that one guy, head gaskets, that was why they tell you they want to yield strength and all this other stuff. Well, those metal head gaskets require a super smooth head. So you might want to not do that unless you're running some sports car and you want to go get those heads planed. That metal gasket might not be a choice. Even the manufacturer tells you that they require a smooth head. See if I can find it in here. So let me try oil. Great. I want to show you that it's really bad. The oil takes it to about 50% coefficient. So can you imagine if you said torque to 70 and you went with the oil, you'd be way into the yield. You'd be way over torquing that thing. And oil as a torque lubricant. I'm sorry, graphite. Graphite was 50%. Graphite's the one that's terrible. Your oils are 35 to 40, 30 to 40 right here. 35 to 45 and 30 to 40. This is your lubricant effect on bolt tension and torque. It's going to increase it by this much. So that guy should soak it in oil. So you're going to now take the torque numbers from 65 following his device of an engine manufacturer. So where are you guys here? You hear from me? So following your following your advice. Oh wait, I don't have my phone with me. Oh, here it is. Following your advice of that guy, the engine manufacturer, or a shop. Start for 65, and then I can choose to add. Well, because he didn't tell me which one. Let's say I made a mistake and used some 10W40, and I'll go with the high range, or I can go with the low range. I now did 19.5 to my numbers, so plus 65. I just changed the manufacturer's torque recommendations from 65 to 84.5 by using oil. Now, if you were if you were reusing those bolts, as you follow the device of all those other people, you've now maybe popped the bolt off inside your head, and that's all because you try to save, $40, $70, $90, whatever it might be. If you had a torque bolt, the one to that point, let's see. Your comments, Toss. Yeah, you can use some anti-seize, if it can take that heat range. They sell it anti-seize with heat range. Oh, wait a minute. So Doss, we'll do that one then. We'll take a look at it real quick. That heat range. So you come over here. I'll put the links down there, but you'll grab, this shit's not cheap either, Doss. Anesthesia is not cheap, but this one might meet your range requirement. Yeah, this one takes up to 2,400 degrees. And you would match it up with whatever your heads are, what you're trying to match, Doss. See the different materials. If you can go to Loctite yourself, but I can give it to you also. This one has no metal in it, so you don't have to worry about. You want to try it with no metal because you don't want this damn gulling to happen. Gulling. That gulling is can lock that shit in there, freeze it in. It's called like cold welding is what it's typically called. So here's your coefficient. You do not want to mess with that oil. It's going to go crazy, jack your scale up. And here's your proof. Here's your yield. Here's your ultimate clamp load angle. And you saw your clamping went way down too, Doss, when you added that oil. Because you got a false set, if you will. A false set. Let's go back to that now. So there is the engine, the 5.7 engine, 7/16 bolt, grade 8. It's typically you torque that. If I was just going to recommend, standard torque, metal to metal, steel to steel, I would say, yeah, you're good to go. You can torque that around. I would recommend to you, 70 pounds is going to give you a right torque on that bolt to give you a clamping force. 70 pounds. Look what the manufacturer apparently says of Chevy. And we'll slide over to that. "65 foot-pounds. So if you're using a Chevy and you just tore the heads off and you only had them off for a limited amount of time and you want to give another shot at it, yeah, go ahead and give another shot at it, I would say. 65 foot-pounds, crank it up, give it a shot. With that said, if you've got some old head bolts, the same old head bolts, I would take them, put them somewhere that I can, create a bolt system that you can create that you can torque the hell out of it. And you got to create your own way you're going to do that. Where you're going to weld it into something or that nut or bolt, whatever you're going to do, and try to see what its failure is from the old head bolt. Maybe I'll do a video on that. Maybe I can find an old engine and just go in there and prove the breakage is not going to happen under retorquing your cylinder head bolts. That'd be kind of awesome. I go to a junkyard. I'll pay the guy like $10. Let me go out there and rip a head off, and then crank down the thing and show failure on the video. That would be kind of cool. to show that pulling it out, cranking it in, pulling it out, cranking it in, because we don't care if it locks into that head. He'll be throwing it in the trash. But you see what clamping force, 745. And we can change this to 30.30 with the other oil. And look at my clamping force, 495. So it's about the clamping force. All those extra bolt locations that will give you a combined clamping force to keep that block in place. All right, so this is about the end of the video. Just giving you a quick rundown. It's your decision. You can base it on real facts over here, if you will. I would say science, but science is kind of fake now, so I hate aligning myself with science. So you're going to base it on real facts or data. You're going to figure out your head bolt size. What kind of metal you're going into. Is it metal to metal? Ideally, you want to be metal to metal. This is 70% of yield strength. You're going to have to leave a margin of error in there. So it's 70% of yield strength. This bolt, 7/16, is 52 foot-pounds. And tying it into the Chevy engine, 65 foot-pounds are what they want. Now, of the yield strength. So I'm not there yet. Now, if I take it up to 65 pounds, I come up with roughly about 113,750 PSI that I'm applying based over once I step it up to 65 pounds. That's my rough estimate on the metal I was using, materials, and it's just my estimate. But I'm at 113,750. What does 113,750 do for me? Yep, sorry guys. 117, I'll repeat the numbers. Wait till I get to my thing. So under the grade 8 bolt, I still need the other to find that bolt. See, this one's punching out at 120 on the proof on it, right? That's everywhere from 1/4 inch to 1.5 inches. And using this scale, where the hell's my scale at? Yep. I keep going around in circles. I keep going one up, and I'm missing it by one, aren't I? Each time. Well, apparently, I got rid of my scale on my ass. I'll tell you the numbers anyway. I was at, let me look at my math on that. I'm still under. I have not reached the yielding of that bolt. I could be looking right at it. I wouldn't see it, right? The way I'm doing this right now. I'm at 113,750. I'm just going to use this number for you guys. You guys can find your own scale. All right, so I'm not even reaching the proof load yet. I have not crossed into the yield. This bolt is functional on and off. I can pull those heads off, put them back on with my confidence that that bolt's still good to go under those temperature ranges. I need to research that bolt, though, to figure out that manufacturer of that bolt. When they heat treated it, did they, how did they do the heat treatment? Because I got to make sure that whatever they did, that the heat treatment is not affected by 200 degrees, which I know they're not, but I'm anal that way. I would check it out still. And we're still good to go. Oh, there we go. No. This is this system is, what is this system here I'm looking at? Proof load tension for grade 2, 5, and 8. Coarse thread. UNRC. I just look for 8, grade 8 mostly, and it's UNRC. I don't like that on there. What are the UNRC? Do not use the scale. The scale is specific to something else going on here. This might be not a regular 8. This might be like an 8A or something, because these numbers are way too low. You know, unless they mean 128,000. You know, even the two of them, they don't make sense to me. Proof load pound. No, it's not even PSI. It's not PSI. Yeah. All right. So that's okay. That's probably going to be its clamping or shear value, even though it didn't say shear. That scale, I wouldn't trouble you on that one. For fun, I might get hold of a manufacturer. Actually, I have to. Curiosity's killing me. All right, so I can't show you. Obviously, I can't show you the last one I wanted to show you, which was the darn proper scale. We're up to different AHTM 490 on those other bolts. It was something else I had to research, and then I decided to come over here. They were no longer using A325s anymore. They're gone. That pretty ass bolt. Proof strength 120, 130. This is going to be your bolt there. All right. So you see, I'm way below it. I can recycle that bolt not as much as I want, but within how I feel comfortable. Do not put it in oil, or you just blew it. You're just killing it. So no oil. Use the charts that I'm going to give you. Race them, figuring out what your torque pressures are, what your torques are rather. I said pressures. I'll give you this chart. Don't let this be the end all. This chart is not your end all. Your metals matter. Your vibration, all that stuff is matters. Is material going to heat up? What degree and all this? This is not your end all. This is just a little peek into how you're lining up. You want to make sure your bolts are the proper grading. That they got nice, good, clean threads on them before you install it and clean it out. Also inside your block, you want to make sure that's beautifully cleaned also. Blow it out, clean it out. Don't oil those threads. Don't oil them. You won't know, you won't do it properly. You want to know, I guess you can try something crazy. It doesn't work that way. I mean, you try to twist, yeah, no. The problem is you'll be almost bottomed out if you oil them, when you can almost hand screw them all the way in. That's not a good thing. The torque was calculated that. Now this guy believes that, this one here believes that guy, the engine guy. Well, it's 80% of it's lost on just friction going into the hole. Yeah, but you have to then back it back out if you're going to use lubricant. You've got to use the coefficient factor. And you got to trust that you're doing the proper coefficient factor. Which one are you going to use? 30 or 30 coefficient or 40. But even when you do use it, you're still dropping your clamping force. I know you said, well, it doesn't make sense because you're increasing you're going back to 70 no matter what. Well, that's not the way it works. It's not the way it works. All right, I can't find it, damn it. Doss, tell me about your thing real quick. I missed your message. Yes, the threads change on torque. They elongate. So here's a question. They elongate. Oh, no, wait a minute. The threads become like mini shims. They become like locking it in, and the elongation is happening in the bolt from the top of the thread back to the top of the bolt head is where your elongation is taking place. Hopefully there's enough threads on there where no elongation is taking place in your threads. If they were, you'd be ruining your where you're going to thread it in again. Those two threads interlock and they become one with that margin of error I showed you. So this is a rolled thread, and when they heat it, it'll come out to the same size again, and it will balance itself out. But this interlocks with the walls that you're screwing into, and this is what grabs the wall. Each one acts like a shim. They're pushing back on the wall all equally with those tolerances I gave you of like 0.69, within the 4 digits of tolerances, And as you're still cranking, it's still trying to pull down. It's still turning downwards as it's doing with the torque going down into the hole. This is elongating back here by that micro bit, creating that torque. That's where it's happening. Now, the friction, it has to overcome the friction of it rotating down each one of these, the mirrored or married surface that you're pushing it. It's got even more force on it as you go down. But that's calculated in the formula for your torque. That friction is calculated. And you just crank it on down. Unless they tell you to add, your manufacturer tells you to add, this Loctite product by this much amount, etc. If you take away that friction, you can't get torque. It's just going to keep coming down. It's going to lock in, right? So now you're fully closed. Imagine that. So you're fully down inside the threads. I have another image, better image of that. I think I have an image with both of them interlocking. Both of them interlocking. Yeah, this works for me. So where are you? I hope I got you, Doss. Let's see. Make sure you're over there. Good, got it. Yeah. So, but the oil. So we talk about the oil right here. Then I don't know. I guess you can pick either way. I kind of want to consider going that way, and then I'm torquing from this end down here, and we're pulling down. I guess we can pull up. Doesn't matter. There's that tolerances they allow, but when you're cranking, they're all will bounce against. They're all, in theory, should be hitting each other. They should all be in contact with the forces. This changing. You're not lifting up the engine, right? So this is the only thing changing is this. This will not be changing. So as you crank down, as you're cranking down, the forces then are come back on the back side of this, all the way on all of them. 1, 2, 3. Not on the bottom side, right? It's the top, 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 top. And as you're cranking down, this elongates. All that friction is calculated, as everyone likes to say. 80% of it, 80, 90% is in friction, and the other 10% is your is actually the tightening of the clamping action of the bolt. Well, okay, but now if you add oil in all this, it still want to glide across these threads. That's what pistons do, right? They're going all the way up and down that shaft, thousands of times a minute or whatever it is. However depending on the engine is. That oil really lubricates it, lets it ride. Well, the same thing's going to happen here. It's going to take you a long time to create that same 70 pounds of friction, torque, because you're going to be gliding along here. And it's going to be like, no, we don't feel anything yet. We don't feel it. But yet this thing is still going to be going down. It's going to be in here. It's going to be elongating in here because it's only designed to feel the friction. It doesn't feel the elongation in the bolt. If I hope I'm explaining that to you. It doesn't feel it. Torque wrench doesn't feel it in there. It feels it on the resistance. And if it doesn't feel the resistance, it just keeps spinning around like it's like a car and a piston engine up and piston inside the motor, nice and lubricated, until you finally make it. Tell it it's 65 on foot-pounds, and that's why the lubrication really changes everything. So what else I got for you? I hope that was a good one. Hope you got that one, Doss. That's it. I'm going to terminate that little lady. I'm going to terminate this one, Doss. I'm going to terminate this one. Nice hanging out with you. So in conclusion, do not use your head bolts unless they can meet those criteria. That perhaps you've tested one of them. Previous head bolt that you had sitting around. Be very cautious about your lubricants. Really cautious about those lubricants. You do not use a rusted bolt. Clean your threads. Ideally, you want to, each one turns in the same amount of distance. You can clearly retap this. They are not counting on you having junk in there, so that can give you a false reading. As you crank in, you can get a false high torque reading if you've got junk inside these threads, either side. Yeah, very. Thanks, cool, Doss. But that's with everything, and with all this stuff, with all your bolts, nuts and bolts. Oh, good one. Good tip is heat. Do not use a torque. What do you call it? A driver to put these in. They create heat inside the threads. The heat inside the threads will give you a false torque reading also. Also backing it out when you do that. If you do it real fast, you can create so much heat that you could screw up a aluminum head, for example. So you can loosen it with a torque wrench if you want to break it free. But then you should go back to just old school, crank it out and crank it in old school. No heat, you keep the heat way down that way. And you'll also feel if you're ever coming into gulling. If you use a power wrench to go in there, you could run too fast, of course, mess it up. Or you could run into some gulling and lock something in here, and next thing you know, you pop your bolt head off. That gulling is nasty. That's what's popping your bolt heads off when you're going in, and all of a sudden you lost a bolt. If you were to rethread it, I'm almost sure, I'm 100% sure you can then say it wasn't this surface here, that it wasn't gulling happened. It was a defective bolt. In that case, you should be kind of happy that it broke its head off. But I'll never have a head break off if you retap and make sure you got good threads here. You won't have an issue. And also, don't use a power screw, and you cannot. It's almost impossible to do the cross thread these. Finally, this angle here, if you've got a bolt you're putting in, and the craftsmanship shows that it's the starting bolt, the starting thread has this out on it, then you need to knock that down. It's not your strength anyway. Knock it back on a bevel, because that is going to be cutting into your threads as you roll around. That's not a good thing. You want to have that knocked down. So make sure that's knocked down. Take a file to it. Go all around the edges and get this tapered edge all around there. Of course, the back side, you want this deck clear wherever you're coming down, because your torque readings will be false also. And your back of if it calls for a washer, make sure you use a structural washer, because it can be compressed. Those washers can be compressed, and you can wind up getting a funny thing going on there. Some of them require a compressed washer, so it's also something to consider. I think I hit all those points. Looking at my notes real quick. Flathead, tap for blind holes, taps. I showed that. Always have a tap ready with this stuff. Anything you got to have a tap ready. Taps. Always inspect your threads. Always when you use your wiring brush on your threads, make sure you don't leave fiber behind on the brush. Blow out the hole